What up, math nerds? Part 1, Assorted Tools to Study the Structure of the Real Numbers. So in this video, we're going to learn some basic tools to talk about the real numbers. Let's go over notation. First up, the natural numbers, this fancy n with the double bar. This includes the number 0, but otherwise just counts up 0, 1, 2, etc. The integers includes negatives. The rational numbers are ratios of two integers, so p and q both have to be integers. P is called the numerator and q the denominator, and the denominator can't be 0. R is the real numbers. This is really what we're going to be focusing on. Now we can use z with a superscript plus to talk about the positive integers, so this excludes 0. Notice this is slightly different from the natural numbers. The convention as to whether or not 0 is considered a natural number does change according to whom you're talking to. I include 0 as a natural number, but it's not a positive integer. Now we can also use this plus on the rationals or the reals to talk about positive rationals and real numbers respectively. The real numbers in earlier work we constructed as Dedekind cuts of the rational numbers, or perhaps you just skipped that and came right here. This amount of detail, the Dedekind cut construction of the real numbers, honestly, it's not that common. So if you just came right here, that's totally fine. Okay, we can intuitively understand the real numbers as the real number line. So you are presumed to be basically familiar with what real numbers sort of look like and behave like, including things like adding, subtracting, multiplying, dividing, how to work with inequalities, and every once in a while we might talk about something like exponential functions, logarithmic functions, or trigonometry, although I'll be honest, they're not going to come up very often. Okay, let's talk about some sets. We want to talk about sets of real numbers. So two sets, capital A, capital B, are said to have the same cardinality if there is a bijection in between them, some function going from A to B, which is both injective and surjective. Okay. If a set has the same cardinality as a subset of the natural numbers, in other words, you can put it in a bijective correspondence with a subset of the naturals, we say it's a countable set. If it can be put into a bijection with the natural numbers themselves, we say it's countably infinite. If it's countable but not countably infinite, in other words, it is in a bijection to a subset of the naturals but can't be put into a bijective correspondence with all the naturals, then we say it's a finite set. Okay? And if a set isn't countable, so it can't be put into a bijective correspondence with the natural numbers or any subset of them, we say it's an uncountable set or an uncountably infinite set. So, how could a set be uncountable? It can't be put into a bijective correspondence with a subset of the naturals or the natural numbers themselves, so in a sense it must be bigger than the natural numbers, but the natural numbers are already an infinite set. They're a countably infinite set. So what does it mean to be bigger than an infinite set, and does that actually mean anything? The answer is yes, it definitely does. Okay. We will deal a lot with uncountably infinite sets. Okay. A useful theorem to have in our back pocket: a set is finite. Remember, a finite set can be placed into a bijective correspondence with a subset of the natural numbers, but not all of them. A set is finite if and only if it can be placed into a bijective correspondence with a specific type of subset of the naturals, specifically the natural numbers 1 through n. If n is 0, we understand that the set beginning at 1 and ending at 0 is the empty set. But in this case, we say that the set A has exactly n elements. If you can place it into a bijective correspondence with the set 1 through n, and notice if n is 0, there are no such natural numbers, and that's the empty set. It has 0 elements. Okay, we're not really going to give a proof of this statement. It's really not terribly complicated, but it's basically an axiomatic set theory exercise, and that's just not the focus we're going to go with. So work through it on your own if you like. Otherwise, take it as a given. A finite set is exactly something that can be listed out, placed into a correspondence with 1 through n. So let's look at an example of establishing a cardinality of a set. So we have a set here, A. The elements are 4, 19.1, and 31, and we claim this set is finite. However, the integers are countably infinite. So we're going to look at a specific function. F of 4 is 1, f of 19.1 is 2, and f of 31 is 3. This is a bijective function between the domain A, 4, 19.1, and 31. Those can all be plugged into F. And the set 1, 2, 3, that's what we get out. Everything in that set 1, 2, 3 is gotten out, but not twice, so it's injective and surjective. Therefore, we have a bijective correspondence between our set A and the set 1, 2, 3. So based off the previous slide, that means we have a finite set with 3 elements. But what about this function g, which I claim is a bijection between the natural numbers and the integers, even though the natural numbers are a subset of the integers. If you plug in a number bigger than or equal to 0, you output 2n, but if n is negative, you compute 2n plus 1 and then multiply that by negative 1. So let's take a look at this function. Okay, so I'm going to list out all of the, well, not all of course, but some of the elements of the domain. So here's our domain, which was the integers, and our range, hopefully, is the natural numbers. So our domain, I'm going to list out by saying things like -3, -2, -1, 0, 1, 2, 3, etc. And we'll sort of see the pattern that goes in here. Now remember, g of n, if you plug in something bigger than or equal to 0, outputs twice that number. So if I plug in 0, I get out 0. If I plug in 1, I get out 2, 4, 6, and so forth. But if you plug in a negative number, you compute 2n plus 1, and then you multiply by -1. So if I plug in -1, I compute 2n plus 1, and then I'm going to multiply by -1. Up here, we were just doing 2n. So if we plug in n equals -1, this is going to output a 1. If we plug in n equals -2, this is going to output a 3 and a 5, and so forth. So observe, when you plug in numbers bigger than or equal to 0, you're getting out all of the even natural numbers, but when you plug in negative numbers, you're getting out the odd natural numbers. So in fact, every number is output exactly once in the natural numbers. This is a bijection. So do the following sample problems. The first set's finite, the odd integers are also countably infinite, and the rational numbers are actually countably infinite. So hopefully you paused the video and gave those problems a shot. Now here is where we see what uncountable sets are really going to be useful for. The real numbers are an uncountable set. So unfortunately, the proof of this is kind of beyond our scope. It's pretty easy to find many proofs online on YouTube. The proof is called Cantor's diagonalization argument. Now the reason we're not going to do it here is that the proof, either historically or in its modern forms, tend to rely on knowledge about decimal or binary representations of real numbers. And we haven't discussed those, so I don't really want to rely on things like decimal forms of numbers in order to prove something about the real numbers, because we haven't talked about decimals. So since we haven't discussed that, I don't want to use it, but do know that the real numbers are an uncountable set. Now let's talk about subsets of the real numbers. Intervals are a particular, useful, and special sort of subset of the reals. So if you have two real numbers a and b, you define intervals with certain inequalities. So for example, if I put the square bracket on the left, a comma b, and then a parenthesis on the right, this means everything bigger than or equal to a, but strictly less than b. You could also put an infinity or a minus infinity, which just means that side of the interval doesn't really get a inequality. You can also put square brackets on both sides and infinity on the right, etc. Okay, we're all pretty familiar with intervals. Just remember that intervals are defined in terms of inequalities. One thing to point out is that my convention for writing intervals might be slightly different than other sources. For example, we can fairly easily represent the empty set as an interval, because I can write an interval of the following form. Okay, maybe I put a bracket here, 10, 6. This represents all numbers bigger than or equal to 10 and also less than 6. And there are no real numbers bigger than or equal to 10, but also less than 6. So this is an empty set. I could also put the real numbers themselves to be an interval of the following form. Okay, this is not terribly objectionable, and it is pretty common. Another thing that's maybe a little unstandard is that a set with a single element can also be represented with an interval in this way. For example, if I do this, I want everything bigger than or equal to 10, but also less than or equal to 10. What real numbers could possibly satisfy both of those? Exactly 10. So with this convention, I'm allowing an interval to just represent a single point. That is a little non-standard. It's not a terribly important result. Okay. Whether you take these non-standard intervals as intervals or not, just observe the complement of an interval is either another interval or maybe two intervals. So a useful theorem about intervals, this is pretty quick to understand why it's true, but it's very useful nonetheless. If you have an interval and 2 points in that interval, x and y, let's just suppose x is the smaller one, then any number in between x and y is also in the interval. Any 2 points in an interval, everything in between them must also be in that interval. So the proof is, by many, many cases, honestly, based on what sort of form the interval has. Let's just assume it is what's called open on both sides. So all we have to do is show that any 2 points in the interval x and y, everything in between them is also in the interval. In other words, the interval from x to y is also in the interval. So pick anything in the interval from x to y. Well, since x is less than y, we have a is less than x, less than y, less than b, because x and y are both in our original interval from a to b. Those are our outer endpoints, and x was smaller than y. So if z is in between x and y, we can pretty easily squeeze it in between. Okay, so this inequality and this inequality came from the fact that x and y are in the interval. This inequality right here was something we assumed by picking z to be an element of the interval from x to y. And now that I have all of these intervals, what do we do with it? Well, I get rid of the middlemen x and y, and I just claim a is less than z is less than b, which really was the definition of the interval I, everything in between a and b. So very quick, totally understandable proof, very intuitive result. When you're dealing with intervals, anything in between 2 points in the interval must also be in the interval. We can also do things like add sets together. If I have 2 subsets of the reals, I can define a plus b to be all x plus y's, where x was an element of a and y was an element of b. And I can do a times b, which is all possible products. Notice a plus b is not the union. We can already do unions. We can already do intersections. This is different. This is adding things from a to b. Okay, you can also do a plus a constant or a constant times a if you just consider a single constant like the number 8 to be the set containing the number 8. So, as an example, we've got the set 1, 2, 7. I want to add it to the set 1, 2, 3, 4. And I claim the result is 2, 3, 4, 5, 6, 8, 9, 10, 11. Notice we're definitely not taking a union. So, how do I construct the sum set? We take everything from one set and add it to the other set. So we need to pick every possible choice from 1, 2, 7, and then add it to something from 1, 2, 3, 4. So taking the left to be a choice of 1, 2, 7 and the right to be a choice of 1, 2, 3, 4, these are all the possible choices we can make, and observe what we get out. Going column by column, 2, 3, 8, 3, 4, 9, 4, 5, 10, 5, 6, 11. Once we get rid of redundancies, like 3 and 5 are both in there twice, as was 4, the possible results are exactly 2, 3, 4, 5, 6, 8, 9, 10, 11. This is all possible sums of something from the set 1, 2, 7 plus something from the set 1, 2, 3, 4. Observe, by the way, that 1 is not a possible sum. Even though 1 was in both sets to begin with, since you have to add something from one set to something to the other, in this particular case, we could not get out 1 as a possible sum. A more interesting example, however, would be this one. If I had a less than or equal to b and c less than or equal to d, suppose I take 2 intervals and I'm just going to go ahead and work with the closed ones, a to b and c to d. Now note these are not empty sets because I did assume a was less than or equal to b, so the interval from a to b does contain numbers. Similarly, the interval from c to d is not empty. If I want to add these together, I actually just get another interval. The left endpoint is just a plus c, and the right endpoint is just b plus d. But once we say it, we've got to prove it. And we're going to prove this the same way we typically prove set equality statements, by mutual containment. So let's show that the left, the interval AB plus the interval CD, is a subset of the right. So take something from the interval AB and something from the interval from C to D. Since x is in between a and b and y is in between c and d, we find that their sum must be in between a plus c and b plus d. Therefore, anything of the form something from AB plus something from CD. In other words, anything in this set, anything of something from the left interval plus something from the right, must be in between a plus c and b plus d, so it must be an element of this thing here. Therefore, the left is a subset of the right. Now we have to go the other way. Now we're going to go the other direction. We're going to start with an element of the interval from a plus c to b plus d. So I have an arbitrary element of this interval, so it's bigger than or equal to a plus c, it's less than or equal to b plus d. Since it's bigger than or equal to a plus c, I can write it as a plus c plus a non-negative extra term. Now, if this extra term is less than or equal to d minus c, so z is of the form a plus c plus something, but the something we're adding on is less than or equal to d minus c, well, all I have to do is add c to this inequality right here, and I'll get c plus d is less than or equal to d, but c plus d is definitely bigger than or equal to c because t was bigger than or equal to 0. So this thing here is in between c and d. Therefore, I can write z as a plus c plus t, something from the interval from a to b, specifically the left endpoint, and then something that we just showed is in the interval from c to d. So it must be something from ab plus something from cd. That was under the assumption that t was less than or equal to d minus c. Well, what if that isn't true? So if t is actually bigger than d minus c, now since I know it's bigger than that, I'm going to write t as d minus c plus something. Since the element we started with z was a plus c plus t, and I've just written t in this form, okay, notice the c's cancel out and we get a plus s plus d. So the thing that we added on cannot possibly be bigger than b minus a. If it were, okay, if s was bigger than b minus a, then a plus s plus d would be bigger than a plus b minus a plus d. This would be bigger than b plus d. However, what did we assume about the element z that we started with? We started with something that was not actually bigger than b plus d. So s can't be larger than b minus a, therefore, back down here, s is less than or equal to b minus a. So now I've got z is of the form a plus s plus d, but s is less than or equal to b minus a. So if you make that substitution in here, you'll get a plus s is less than b. So I have something in between a and b plus d itself. Therefore, it is something from this interval plus something from this interval. In either case, we found that the element z, which was taken to be an arbitrary element of this interval here, can be expressed always as something from ab plus something from cd. Therefore, the interval a plus c, b plus d is a subset of the interval ab plus the interval cd. And since we have shown both directions of set containment, the two sets are equal. We have established this claim back at the beginning. Now, this result is pretty intuitive. The sum of two intervals can be computed totally easily. Is it really necessary to go through all of this work? Yes. Okay. Because there are lots of non-intuitive results about how sets get added together. There are lots of things like if I took the interval, say 3, negative 6, and I multiplied it, sorry, let's do negative 3, positive 6, so it's a non-empty interval, and I multiplied it by the interval negative 1, comma 4, if I just said, let's multiply the endpoints together and get 324, that's totally wrong. This is not true. How do I know that? Well, I'm going to take something from this interval on the left times something from that interval on the right. Notice that 0 is in both, so I can do 0 times 0 and get out 0. So whatever the result is, it needs to include 0, and this interval didn't. Okay, so just basing your results off intuition alone might lead you to false results. So yeah, we always have to go through the proof. So do these following sample problems, okay? A, B, C, D, K, all real numbers, etc., etc. You can read them, pause the video here, and try to work through these. Also, try to develop similar statements for these problems if some of the numbers are actually negative. So hopefully you had some luck. And yes, we see that when numbers are positive versus negative, some things don't quite work out how you would really hope. There isn't a fixed pattern. You actually do have to work through and see what happens. Never state things as if they're facts if you're not prepared to back them up with proof. Now, I mean, okay, we can't always work back 95 million steps back to the basics of set theory, but in general, you really do need to back things up somehow. An important thing to consider is that not every subset of the reals is an interval. There are many ways to construct sets that are not themselves intervals. For example, the integers, definitely a subset of the reals, but not an interval. How do I know it's not an interval? Well, in between two integers, for example, 0 and 1, there are many numbers that are not integers, like 1/10. So since I can find two elements of the set, and not everything between them is in the set, it can't be an interval. But the integers can be expressed as a union of countably many intervals and complements. You could also throw intersections in there if you wanted. So try to think, how can I express the integers as a union of infinitely many different intervals? The rational numbers as well, not an interval, but can be expressed as infinitely many intervals and their complements with unions and intersections thrown in. Try to think about how to do that as well. But there are even weirder subsets of the real numbers that cannot be constructed as countable operations on intervals and complements with unions and intersections. We're not going to get into constructing them, but they do represent practical things. These exotic subsets can lead to some really interesting results. More importantly for us, just don't think intervals are the only things around. If we talk about subsets of the real numbers, intervals are handy things to picture and they are handy things to draw, but know in your heart of hearts there's more going on. Moving along, let's talk about the absolute value function. This is something it's useful to be able to work with. Many students think they know everything there is to know about it. It is a piecewise defined function. The absolute value function is not just make the number positive. That's not a statement you can work with mathematically. We should really have a formula that we can base it off of. Therefore, we can write down this equation and work with it to do proofs. The absolute value function, if you plug in a number bigger than or equal to 0, the output is just what you started with. If you plug in a negative number, you multiply it by -1. There's the absolute value function. Do not make the mistake, by the way, and this is very, very common. If you see a number written like this, that does not mean the number is negative, just because it has a negative sign in front of it. And if you see the number x written down, don't assume it's positive because it doesn't have a negative sign in front of it. So let's prove something about the absolute value function. For any real number, the absolute value of -x is equal to the absolute value of x. Intuitively obvious, but let's go through the proof. Well, I can start with three possibilities. Either x is 0 or positive or negative. Well, if x is 0, -1 times x is also 0. And in this case, yes, the absolute value of 0 is 0, which is the absolute value of -0 because that's still just 0. So if x happens to be 0, then the absolute value of x and the absolute value of -x are the same. Let's move on to the second case. If I start with a positive number, then -x is negative. So the absolute value of x is x. Now, how do I know the absolute value of x is x? Because x is positive, and that's how the absolute value function works. But since -x is a negative number, then the absolute value function says multiply by -1. And now I have -x, that's just the same thing as x. So overall, the absolute value of x was x, but so was the absolute value of -x, so they're equal to each other. The third possibility is maybe I started with a negative number. So if x is negative, then -x is positive. So if I take the absolute value of a negative number, the absolute value function multiplies that by -1. So the absolute value of x is just -x. But since -x is positive, the absolute value function doesn't do anything to it. So the absolute value of -x is also -x. So they are equal to each other. So in all three cases, whether x was 0, positive, or negative, the absolute value of x was always equal to the absolute value of -x, and the result is proved. Similar to that last proof, try to establish the following things. Pause here and work through as many as you can. All right, good work. Moving on. The absolute value function can be interpreted as a distance between two numbers. So the distance between x and y is the absolute value of the difference, x minus y. This function, the absolute value of x minus y, has three important properties based as a function of two variables, x and y. The result is never negative, and the result is 0 if and only if x equals y. In terms of distance, think of this as meaning the distance between two numbers is never negative, and the only way the distance between two numbers can be 0 is if those two numbers were actually the same thing. Also, this is a symmetric function. The distance from x to y is equal to the distance from y to x. And finally, the distance from x to y is less than or equal to the distance from x to z plus the distance from z to y. These three properties have special names. The first one is called positive semi-definiteness. The second is symmetry, as I mentioned, and the last one is called the triangle inequality. It does, in fact, have something to do with triangles. So the triangle inequality says that if you have three real numbers, the absolute value of x minus y is less than or equal to the absolute value of x minus z plus the absolute value of z minus y. If I replace x minus z with a and a z minus y with b, notice then that a plus b, the z's will cancel out and you'll get exactly x minus y, and you'll get exactly this right here is the same as this statement right here. So the triangle inequality can also be written in this bottom form. The absolute value of one number plus another is no larger than the sum of the individual absolute values. This is honestly the version of the triangle inequality that we will generally be working with in this course. Now, what does it have to do with triangles? Okay. It has to do with an interpretation in terms of distance. The distance from x to y, looking up at that top line, cannot be larger than first doing the distance from x to z and then adding the distance from z to y. So the length of one side of a triangle from x to y can't be larger than the sum of the lengths of the other two sides. Let's take a look at what this would look like. Now I'm going to draw a two-dimensional picture, so this isn't really in the real numbers, but if I were to call this point x, this point y, and this point z, the distance from x to y is no larger than first going to z and then going from z to y. This length plus this length cannot be smaller than this one. If you add two sides of a triangle, their lengths together, the result cannot be smaller than the third side. So here's an interpretation of the triangle inequality as it pertains to distances in a triangle. In the real number line, we don't really have two-dimensional triangles, but the inequality still stands. Can we prove the triangle inequality? I sure hope so. So we need to prove for any two real numbers, the absolute value of a plus b is less than or equal to the absolute value of a plus the absolute value of b. Earlier problems that we did give all of these results here. Now the one on the right doesn't look like something that was assigned as a homework problem, but observe if you proved, and this was assigned, that a is less than or equal to its absolute value and b is less than or equal to its absolute value, if you simply add those inequalities together, you'll get this one here. So even though this box on the right wasn't exactly a problem that you did earlier, it does follow immediately from this one, which you did. So since we get all of those inequalities above, if a plus b is bigger than or equal to 0, then what does the absolute value function do? It does nothing. But we already know that a plus b is less than or equal to the absolute value of a plus the absolute value of b. So if a plus b is bigger than or equal to 0, the triangle inequality is there. The absolute value of a plus b is less than or equal to the absolute value of a plus the absolute value of b. What if a plus b is negative? Then the absolute value function will multiply by -1. But we also established this right here as an earlier result. So either way, the absolute value of a plus b is less than or equal to the absolute value of a plus the absolute value of b. And the triangle inequality is proved. Try to establish these following related results. I hope you're pausing. I hope you're actually doing it. Go ahead, comment, like, subscribe, etc. Call for engagement, blah, blah, blah. YouTube terminology. Okay, so did we do these problems? I sure hope so. Now here's an intuitive, but still very useful result. Suppose I have two real numbers. with the following property. For any epsilon which is positive, this is the Greek letter epsilon, the distance from x to y is less than epsilon. So I have two real numbers so that no matter what positive number I pick, the distance between them is smaller than that. Then x must in fact be the same number as y. So assume to the contrary that x and y are not the same. Well, either way, x is less than y or x is bigger than y because they're not equal. Let's just go ahead and assume that x is the larger one. In this case, the distance from x to y is positive. Okay? Since x is bigger than y, if I simply subtract y from both sides, we get this second inequality. So the absolute value of x minus y must be less than any positive number. This was our assumption. The absolute value of x minus y is less than any positive number, which would give us that the absolute value of x minus y is less than x minus y itself. But we proved already the absolute value of a number is always bigger than or equal to the number you plug into it. And in this case, the number is just x minus y. Therefore, x cannot be equal to y, cannot be not equal to y. So if two numbers are so close that the distance is less than any positive number, they have to be the same number. What this really looks like for us is if I have a number y and I have x which is bigger than or equal to y, if they're not the same number, I get a positive distance between them, which means I could have picked an even smaller distance and found something in between the numbers x and y. If x and y have the property that there is nothing in between them, they must have been the same number. Which does mean there is no such thing as the smallest positive number. If I thought, oh, let's suppose x is the smallest positive number, then the distance to 0 is so small that nothing else can be fit in there. There is nothing in between 0 and x. But what did we just show? If there are no numbers in between 0 and x, then 0 and x are the same number. There is no such thing as the smallest positive number. A lot of students like to start working with proofs later on by saying things like, oh, suppose x is the smallest positive number. Or, oh, suppose z is the first number bigger than y. There's no such thing. If two numbers are not equal, then there is a whole interval of numbers in between them. Yes, numbers are always kept apart from one another by an entire interval, which is an uncountable quantity of numbers in between them. So that'll do it for this time. I hope you enjoyed it. Come back next time. We're going to keep talking about the structure of the real numbers.